Okay, Sophie, I think we're live.
Okay, fine. So good afternoon, everyone. I'm very pleased to chair this fifth session of Computer Science Logic 2029. So we'll have 4 talks this afternoon. The first talk, entitled Game Comonads and Generalized Quantifiers, will be presented by Adam O'Connell. Please, Adam, you can start.
Sorry, I think my talk is pre-recorded, so is Alex setting that up, or do I have to do something?
I think Alex is setting it up. He might have forgotten to unmute.
We do not hear.
Alex, you're muted. I think that might be the cause.
So, Alex, maybe you should unmute.
And welcome to this CSL 2021 talk about my paper, Game Comonads and Generalized Quantifiers. My name is Adam O'Connell. I'm a PhD student at the University of Cambridge, and together with my supervisor Anuj Dawar, we've been using category theory to look at results from finite model theory and descriptive complexity theory in a new light. So today in my talk, I'm going to be telling you, first of all, a little bit about the history of the area of descriptive complexity theory we work in, and in particular, the importance of games in that story. Secondly, I'll be telling you about game comonads, which is a very new approach to some of these logical games, and in particular to controlling logical resources, as we call them. Then I'll be telling you a little bit about generalized quantifiers, which are a very powerful type of resource used in logic. And finally, I'll be giving you a little bit of a flavor of how this comonad that we construct in this paper is built and what opportunities and avenues of research it opens up for the future. So to understand this paper, we first need to understand the world of logic, complexity, and games. And that starts with a brief tour through the world of descriptive complexity. Now this begins in the 1970s with a result of Ronald Fagan, which for the first time connected a complexity class to a logic, meaning that he proved that, well, a class of finite structures is only decidable in NP if and only if that same class can be described in the logic existential second order logic. So this created a very interesting area of study where we could relate complexity classes to logics, and it really opened this big question of whether there is an equivalent logic for polynomial time. Now, in the 1980s, this was conjectured by Gurevich to be false, that there is no such logic, but we're still working on this today. And in fact, there are still candidate logics where we don't know a class that can be decided in p-time that can't be described in, say, ranked logic or in choiceless polynomial time. So how do we prove lower bounds on these logics becomes an interesting complexity theoretic question. And the way we prove these lower bounds is using games, and in particular, using a type of game known as a spoiler duplicator game. Now these games, as the name might suggest, are played between two players, spoiler and duplicator. And in addition, they have access to two structures A and B, which will share some relational signature sigma. And the way these games unfold is that spoiler is, in one version of the game, going to provide some sort of evidence that there is no homomorphism between A and B. Duplicator is going to respond by saying, by refuting that evidence in some sort of way. And we'll say that Duplicator will win these games. If Duplicator can win these games, that's going to be true if and only if all the sentences in some logic L that are true in A are also true in B. Now, there's also two-way versions of these games where the evidence provided will involve more of a kind of two-way approximation of isomorphism, and Duplicator will win these if and only if there's a logical equivalence between A and B. And the exact logic L is really going to depend on what the rules of these games are. So let's start with an example of one of these games so that we all know what we're looking at. So here we present the Ehrenfeucht-Fraser game between two undirected graphs. Here, the pentagon and the hexagon, right? And in round one of this game, spoiler is going to choose some vertex of the first graph. Duplicator responds with some vertex of the second graph. And rounds will continue like this. Spoiler picks something from the first graph, Duplicator responds on the second graph. And now how do we decide whether spoiler or Duplicator has won? Well, at the end of each round, we're going to look at the evidence that's in front of us and check whether it's evidence for or against a homomorphism. So in round 2, for example, we have this partial map from the left to the right, and that is indeed a homomorphism. But say we played the game for 5 rounds, we might end up with a situation that looks like this. And the map, which we can see because there's a edge between A1 and A5, but no consequent edge between B1 and B5. This is a losing situation for Duplicator. So Duplicator can't win this game with 5 rounds. And so as we've seen before, Duplicator winning this implies that A and B are related in some way over some logic L. And the crucial observation here is that the harder we make this game for Duplicator to win, the more expressive L is going to be. So in those Ehrenfeucht-Fraser games, we actually know that the logic involved is infinitary existential positive logic up to quantifier depth k, for if we play the k round version of the game. So we saw before that those two structures are related up to quantifier depth 2, but not up to quantifier depth 5. And now there's lots of other versions of these games. You can have a two-way version of the Ehrenfeucht-Fraser game. We have, due to colitis and Vardy, an existential pebble game where the markers can be moved around on the structures, and that'll be important to our work. We also know, again, important to our work is going to be this game due to Hella, a bijection game which places more constrictions on the Duplicator, but it captures a stronger logic. In this case, the k variable logic extended with counting quantifiers. And Hella goes even further, providing the n bijective game, which is exactly what we study, which extends this logic by generalized quantifiers, which we're going to get to later on. So now we're going to see how category theory makes its first appearance into this world of games and finite model theory. And the first kind of question you might think category theoretically after seeing the last section is, well, you have two categories here, essentially, or two things that look like they could be categories. On the left-hand side, you have the traditional category of relational structures with homomorphisms and isomorphisms. But on the right-hand side, you have this new category which represents these duplicator winning strategies we saw before, which have this sort of one-way logical implication as the arrows and the isomorphisms being this logical equivalence. And naively, you might want to ask, well, can these two things be connected in some way categorically, or can one be built from the other? And this is the question that game Comonads, in a sense, answer, along with many other things. So we first saw these in Abramsky, Dawar, and Wang's work in 2017, which led to the creation of this pebbling comonad. So this pebbling comonad is a construction on relational structures over fixed signature for some parameter k, and what it does is it sort of unravels the structure into this tree-like structure of pairs of elements from the underlying set A and pebble indices k. And the way you should really think of this is as histories of spoiler plays in a game similar to what we've described above. So it's kind of recording all the moves that spoiler could make in this case, the infinitely long K-Pebble game. So for those of you interested in the categorical details, there's a co-unit and a co-multiplication that go along with this as to make it a comonad, but we won't dwell too much on those at the moment. What we are interested in, though, is that some other constructions that come out naturally from the category theory, which are the Kleisli category in one instance, will capture duplicator winning strategies in some of these games we discussed before. So homomorphisms in this Kleisli category are duplicator wins in the existential K-Pebble game, whereas isomorphisms in this Kleisli category give you this winning, this bijection game due to Hella. Co-algebras also play an interesting role. They capture 3D decompositions of our relational structures, which, to those of you familiar with the complexity theory, will know that that's a very important decomposition. So to the question of can we connect these categorically? Well, yes, we can. But the category on the right-hand side is a little bit different, as we've seen. It's now going to be implication in the existential positive K-variable infinitary logic, whereas on the isomorphisms, it's that logic but extended with counting quantifiers. And so this comonad is not just one comonad, but a whole graded set of comonads where the variable K controls the number of variables in the underlying logic. So this was the first, as I mentioned, of quite a few new comonads that have come about in recent years. So this one, controlling Pebble games and the logical resource of variables, was Abramsky, Dawar, and Wang. But since then, Abramsky and Shah introduced this Ehrenfeucht-Frese comonad for the Ehrenfeucht-Frese game we saw above. That's controlling quantifier depth. And they also introduced one for modal bisimulation and modal depth. Now, an interesting thing about the logical resources controlled in this and the Kleisli categories involved in these is that, well, they all follow this pattern. The homomorphisms in the Kleisli category control some sort of existential positive fragment of the logic, so no universal quantifiers, no negation, and the isomorphisms control that same logic but extended with obviously universal quantifiers and negation, but also with counting quantifiers. So we wanted to look at the importance of these quantifiers in game comonads and see, well, is there a way of treating the quantifiers themselves as a logical resource, and how do we grade that? Luckily for us, treating quantifiers as a resource in descriptive complexity theory is not a new idea. So we can build on work that's been done before to try and bring them into the world of game comonads. And in particular, quantifiers have been seen in descriptive complexity theory as a sort of means of adding an oracle to a logic, in the same way that oracles are used in computational complexity theory. And this work goes far back to work by Per Lindström in the 1960s on extending logics by generalized quantifiers. And that's the definition that we kind of run off in our work. So let's have a look at how that works. So we start with some relational structure that lives in some class of relational structures over a certain signature sigma. And we want to know how, within the language of sigma, we could reason about some other class of structures. So we take, for example, some class of other structures that we're going to say we have an oracle to deciding things that are in this class. So this new signature could be, for example, graphs, and the class could be 3 colorable graphs, or we could be looking at the set here of matrices on the right hand side and the class of, say, invertible matrices. So this is a very, very flexible idea, very general way of adding an oracle in. So how do we add this to a logic? How do we create a logical understanding of this oracle? Well, first of all, we need to interpret a structure from over the signature tau from a structure on the signature sigma, and we can use that using a logical interpretation, as we see here. So each of the relations that exist in tau is going to have a sentence or a formula in over the language of sigma. which defines which elements should be related in the new signature. And how does this quantifier then work? Well, if we fill in these auxiliary y variables and we use this quantifier qk to bind any interpretation given over sigma structures, well, really what that's doing is it defines a map from r sigma to r tau, and we say that this sentence now, this new sentence, is true on A with auxiliary variables B if A gets mapped into this class under the map given by B, and it's not true if A falls outside that class. So this is our way of adding in an oracle to this new class K. So how do we control quantifiers that are added like this? This is a question that was really answered by Hella in his 1996 paper, Logical Hierarchies in P-time. And this looks at a very, very powerful logic which takes k-variable infinitary logic and adds in all of those quantifiers that can be made out of isomorphism closed classes of tau structures, where the only restriction is that tau has some maximumarity n. So this game works a little bit differently to the games that we've seen before, in that the person who starts in any round of this game is actually duplicator. And duplicator provides a function, in this case a bijection, that bounds their actions and future moves, to which response spoiler is allowed to move up to n pebbles around on their structure A, and duplicator is already bound by the function they've provided to move their pebbles in a sort of defined way. And Hella proves in that paper this great result, which says that duplicator wins this game if and only if A and B are equivalent under this very, very powerful logic that's extended by all of these generalized quantifiers. So this is the point that we really take on, and this is the logical equivalence that we wanted to explain using game comonads, and we do manage to explain in our work. Now that we have, thanks to Hella, a game for controlling these generalized quantifiers, we can finally get a glimpse at the main construction of this paper, which is a game comonad for controlling these same quantifiers. So to get there, I'm going to explain two obstacles that we had along the way to constructing this comonad to give you a flavor of the proof. The first of these is really the nature of Hella's game, which is by its construction a two-way game, which, as we saw earlier, is a sort of approximation to isomorphism given in logic. But game comonads, they relate really one-way games with a corresponding two-way game. So we needed to figure out what the one-way game of Hella's game would be. And that we got by relaxing some of the constrictions on duplicator, in particular relaxing the bijection that duplicator is required to give down to a function, and also removing some of the more difficult conditions and the winning conditions. That led us to actually a series of 7 different relaxations of Hella's game, all of which we could prove corresponded to different fragments of this logic extended by generalized quantifiers. And in fact, it gave us a way of identifying groups of quantifiers using rules within these relaxed Hella's game. And so our one-way game, instead of just being generalized quantifiers or sort of positive existential generalized quantifiers, it gave us the generalized version of this, which is positive homomorphism closed n-ary quantifiers. And that's what we see here in this result. The second issue in creating a game comonad is more of a practical issue. It's what would this game comonad look like and how do we build it up? In the case of the pebble comonad, this seemed a little bit more easy in that our homomorphisms in the Kleisli category really are just strategies in the game, responses to series of spoiler moves, and that's what we see being built out here and in these slides. However, in Hella's game, it's kind of confusing to even start to think about what kind of structure would denote the series of spoiler moves and how duplicator would respond just using a simple Kleisli map function. So to do this, we actually showed that you could translate these one-way n function games into a special version of the Pebble game, which we called these n-consistent winning strategies for the K-Pebble game. How this worked is something along the following lines. You could sort of see these strategies for the n function game as follows. So duplicator is going to declare a function, and then we're going to play up to n moves where duplicator has to respond to spoiler using this function that they've declared. And duplicator is allowed to change the function that they've declared either every n turns or earlier if spoiler chooses to use a smaller set of things. And we managed to show really that you could capture this idea of these special n-consistent strategies using special homomorphisms in the Kleisli category of PK, and that we could identify these using an equivalence relation on this structure PK. So this leads us to the construction of GNK as essentially a quotient of this earlier construction by Abramsky, Dawar, and Wang. We showed that the Kleisli category has these interesting correspondences with winning strategies in both our one-way version of Hela's game and with Hela's original game for isomorphism. And we also identified some co-algebras, which if you're interested in, you can see more about in the paper. So to conclude, our construction of the GNK comonad has helped us to understand the role of quantifiers in the Kleisli categories of game comonads. We've also showed that new game comonads can be made from old ones using simple game theoretic translations translated into category theory. And finally, we've been able to give a categorical semantics to generalized quantifiers, which are key ingredients to some of the candidate logics for P, which we hope to look into in the future. Thank you for listening.
Thank you very much, Adam. So we have very little time for questions. So please, who would like to ask a question here? You raise hand and then. Okay, so there doesn't seem to be any questions. So I have one, of course. It's a very general question. Thank you for the very nice work. I would like to know if in these Pebble games, there have been already some studies about having games played between spoiler and duplicator with the notion of imperfect information.
So I actually don't know whether there has been work done on this. I know that I was approached sometime last year by Glyn Winskill, who wanted to talk about trying to model some of the spoiler duplicator games that we work on in a more kind of traditional game semantics view of things. And in some of our attempts to do that, imperfect information seemed to be kind of necessary. So I think there might be some sort of link there, but it's not something that I've seen studied extensively in the area. But okay. Yeah, I think there is something interesting to say there about it.
Okay, Adam, thank you very much. So I think it's about time now maybe to move on, unless there is a very short question rising now. Okay, no, so let's switch to the next speaker. Thank you, Adam, again. So I now welcome the speaker, so Elena di Lavore, for the second paper entitled Compositional Modeling of Network Games. So the paper is by Elena di Lavore, Jules, and Paweł Sobociński. I don't know how to pronounce properly. So Elena, I think you should be ready, please.
Thank you for the introduction. Whoops, this was the last slide. Okay, so today I'm going to present compositional modeling of network games. This is joint work with my supervisors, Jules, Hedges, and Paweł Sobociński. I'm going to start by motivating this work with introducing network games, which are sometimes called games on graphs. So graphs in this talk are going to be undirected and can have self-loops or multiple edges. A network game is a game in the usual sense of game theory, but it's also parametric on graphs. So it means that given a graph, we can compute the network game played on that specific graph. To have an intuition about a network game played on a graph, we can imagine a player sitting on each vertex. And whenever there is an edge between two vertices, it means that the corresponding players can influence each other with their choices. So player 4, for example, can be influenced only by player 3, 2, and 5. A famous example of a network game is the tragedy of the commons, where players need to decide whether to invest or not in a common good. If a player decides to invest in this common good, then this player is going to benefit from the common good, but also needs to pay a cost C. So its utility is going to be 1 minus C. If a player decides not to invest, but one of its neighbor does, then this player is going to benefit from the common good, but not have to pay the cost. So its utility is going to be 1. If a player does not invest and none of its neighbors invest, then its utility is going to be 1 minus C plus epsilon, because players are happier with the status quo than they are with paying the cost of the common good. So the equilibrium of this game is that no player invests. Our main result is to characterize network games, or better, a class of them, as functors from a suitable category of graphs with boundaries to a suitable category of games with boundaries. And when I say graphs and games with boundaries, I mean that we can imagine them as graphs and games in the usual sense, but with additional ports to the outside so that they can be composed with other graphs and games with boundaries. Sometimes I will call them open graphs or open games to mean that they have these ports to the outside. We can see this result in the more general context of functorial semantics and compositionality. So the aim of functorial semantics is to find homomorphic mappings, in this case, symmetric monoidal functors, from syntax, which in our case is a category of graphs, to semantics, which in our case is a category of games on graphs. Compositionality means that whenever we can express a piece of syntax as a composition of two parts, we can transport this composition along the mapping, and we can express the corresponding semantics as a composition of two parts as well. This property allows us to build the semantics, so a game and a graph, from the basic building blocks of the syntax, which is graphs. Graphs in real applications are usually quite big, so it is likely to introduce bugs in the process of specifying the semantics from the syntax. So having a standard procedure for this is useful to reduce the possibility to introduce bugs. In order to define these functors, we need to first characterize the category of graphs as a free monoidal category on some generators and equations. So I'm going to start by presenting this category of graphs. The formalism that we will use is that of monoidal categories. So open graphs are going to be morphisms in a monoidal category so that we can compose them sequentially or in parallel. And in particular, the category that we will use is a prop, which is a strict symmetric monoidal category whose objects are natural numbers, and the monoidal product on objects is the sum of natural numbers. Morphisms in props can be represented with string diagrams. So a morphism in a prop from 2 to 1 can be represented with a string diagram that has 2 ports, 2 wires on the left and 1 wire on the right. We represent a sequential composition of morphisms by putting the corresponding string diagrams one after the other. what we represent parallel composition or the monoidal product by putting the string diagrams one on top of the other. The props that we will use are freely generated by a set of morphisms and equations. This means that all the morphisms in these props can be obtained by sequential and parallel compositions of the morphisms that are the generators, and moreover, they're quotiented by an equivalence relation given by the equations. A famous example of a free prop is the prop of finite sets. So the category of finite sets and functions is isomorphic as a category to the free prop generated by a commutative monoid. And this allows us to think of this prop as syntax for finite sets and functions between them. So the generators are these two, 1 from 2 to 1, that is the multiplication of the monoid, and 1 from 0 to 1, which is the unit of the monoid. And additionally, we ask that they satisfy the equations of a commutative monoid, which are associativity, unitality, and commutativity. To have an example about how this isomorphism works, we can consider this function here that is depicted by this string diagram. So to know the output, let's say, of the second element in the domain, we just follow the path from the second input to the outputs. And we see that it ends up on the first output. This means that the second element in the domain is mapped to the first element in the codomain. Before getting to the prop of matrices, we need to do an additional step, which is the prop of matrices. So we take the generators of finite sets, so a commutative monoid, together with their opposites, so a co-commutative comonoid. We put them together and we ask that they satisfy the bialgebra laws so that they interact nicely with each other. And the prop that we obtain is isomorphic as a category to the category of matrices with entries in the natural numbers. Again, to see how this works, this isomorphism, we can read off the entries of a matrix from its string diagram by just counting the number of paths between the inputs and the outputs. So between the second input and the first output, there are these two paths. This means that the entry in the second column and first row is going to be 2. So matrices are very important for graphs because we can encode with adjacency matrices the connectivity structure of a graph. And this is actually the most used encoding of graphs from graph theorists. So given a square matrix, we can read its entries and see what are the edges in the graph. So for example, in the entry 1, 2, there is a 1. This means that there is one edge between vertices 1 and 2. But equivalently, we could have read a 1 in entry 2, 1 of a matrix, and we would have inferred the same edge between vertices 1 and 2. This means that n by n matrices encode more information than the one given by an undirected graph. This is why we quotient square matrices by an equivalence relation that takes care of this symmetry. And we call these equivalence classes adjacency matrices. So we can represent adjacency matrices in a prop as well. And how do we do this? We take the prop of matrices and we add a new generator from 2 to 0, which we call a cup. And we ask that it satisfies 3 additional equations that mean that this cup interact nicely with the previous structure. In the prop that we obtain, morphisms from n to 0 represent adjacency matrices precisely. So to obtain the string diagram of an adjacency matrix, we take its string diagram as a matrix, as we have seen previously in the prop of matrices. and we add it here in this dotted square. And the string diagram that we obtain is the string diagram of the matrix seen as adjacency matrix. And the nice thing of this prop is that it takes care of the equivalence relation. So for example, these two matrices are equivalent as adjacency matrices, and their string diagram are equal according to the equations of the prop. The last step that we need to do before to get the prop of graphs is adding vertices. And we do this by adding a new generator from 0 to 1. And this time we do this without adding any extra equations. The prop that we obtain is isomorphic as a category to a category of graphs with boundaries specified by adjacency matrices. And the details of this are in the paper. But the important thing is that morphisms from 0 to 0 correspond to graphs in the usual sense. And to have an idea on how this works, we can consider this graph with boundaries. If we want to know how many edges there are between two vertices, we go to the corresponding string diagram and we count the number of paths that there are between the corresponding vertex generators. So we see that the idea is similar to the one of the prop of matrices. And the same with edges to the boundaries. We see that there is a path to the boundary. So I reported here a summary of the prop of open graphs before moving on to the definition of the functors, because I think if you want to choose one thing to remember from this talk, this is a good choice. So we have a commutative monoid together with a co-commutative comonoid, and they need to satisfy the bialgebra laws. And then we add a cup with 3 equations. And finally, we add a vertex generator without extra equations. Okay, now we can move on to the definition of the functors. So I'm not going to go into the details of the definition of the category of open games, but important thing to know is that we can represent games in the usual sense in this category, and we can do this compositionally. A typical morphism in the category of open games has 4 ports. 2 of them go to the right, and we use these to model the flow of information that comes into the game, is elaborated, and then propagated forward to the environment. And the 2 ports that go to the left are used to model the utility that comes from the environment to the game and then is propagated back to the environment. The category of open games is symmetric monoidal and has similar structure to the one of open graphs, and this will be useful to define the functors. So a couple of examples of morphisms in open games. So given any function in set, we can lift it to games in 2 ways. One way going to the right to model this elaboration of information that comes into the game, and one way going to the right to model the elaboration of utility coming into the game. In particular, we can lift the copy function from set. And we will use this to model the fact that we need to propagate the information on the choice of a player to the rest of the network. So we need to duplicate it first. And similarly, given a monoid, we can lift its multiplication going in the other direction. And we will use this to aggregate the information on the choices of all the players and to then elaborate it to a utility for a player. And in order to define the functors, we will require that the network games come equipped with such a monoid structure. And we will restrict to this kind of games. We call them monoid network games. So finally, we can also represent a utility maximizing player in open games with an open game of this type. So the moves X are chosen in order to maximize the utility that comes in from this other port. And finally, the definition of the functors. So given a monoid network game, which is specified only by a monoid and two functions, we can define a functor from the category of graphs to the category of games. And then we can evaluate this functor on a specific graph to obtain a game, an open game that represents that game played on that specific graph. So the two things to notice are that the vertex generator is sent to an open game that represents a player. And the second thing is that the rest of the structure is sent to similar structure in open games. And we have this similar structure in open games because we required that the network game is a monoid network game. And moreover, open games have a morphism that is very similar to the cup of open graphs. So we map this cup of open graphs to the cup of open games. To see one last example, we take back the tragedy of the commons played on this specific graph. So we have seen in the first part of the talk how to encode a graph in the prop of open graphs. And then we have seen in the second part of the talk how to define a functor given the monoid network game from the category of graphs to the category of games. And then we can compute the image of this functor on the graph to obtain an open game that represents the tragedy of the commons played on this graph. Again, we notice the two things. First, that the image of the vertices is fully determined by the utility function of the game. And second, that the structure is determined by the structure of the graph. So whenever two players are connected in the graph, they're connected in the open game. So if we follow the journey of the information on the choices of the player, we see that a player chooses a move, and this information gets duplicated to go to all its neighbors. And then when it gets to one of the neighbors, it gets aggregated through this monoid structure with the choices of the other players, and then it can be given to the player to be transformed into a utility. So as a final slide, I summarize this standard procedure from graphs to games. Thank you.
Thank you very much, Elena. Time for questions. So who would like to maybe ask a question now? So it seems that people ask less questions than this morning. Maybe it's because this is the afternoon. I don't know. Okay, so I have a question. I'm not very familiar with this setting, but I'm wondering how much the entire process that you described strongly depends on the representation you make of graphs.
So I think it strongly depends on the representation of graphs and also on the category of games, because as I said, they have a very similar structure. So they have the copying morphism and they have this monoid morphism and the cup that allows us to define these functors. So the correspondence is functorial. But I think this is it's an index of the fact that we chose like the right category of graphs to do this to define these functors.
Okay. Okay, so maybe now people were thinking of other questions. I don't see anyone. So maybe let's take some time maybe to discuss a bit more. Let me ask you how do you see the ongoing work now with what you have achieved?
So I'm sure that we can generalize this approach to more general graphs, kind of graphs, for example. We can do a similar thing with a category of directed graphs by adding new generators. But also we can generalize this approach to other kinds of games, like maybe mixed strategy games with mixed strategies, or repeated games and things like that. And also I find very interesting the category of graphs on its own. So I think we're going to study more how this category behaves, and if it gives us a better insight on how graphs and the composition of graphs works.
Okay, fine. So thank you very much, Elena. So as you know, because we're streaming live, we should fully respect the schedule. So we have, for the moment, we have 4 minutes left. So I suggest that Alex, do you agree we make a break, kind of break, waiting for the right time? Is it okay for you? So please feel free to maybe go to the gather place, but don't be late.
Well, a 2 to 3 minute break.
Yeah, it's very short. It's very short indeed. So please feel free to maybe express yourself now during this short session break. Just want to be sure Merlin is here. Yes, Merlin is here. Okay, should be fine on time. Okay, so let's meet in 2 minutes. All right. Okay. Okay, so let's resume. So welcome back to the fifth session of CSL, and we are now going to listen to the third talk given by Merlin Göttlinger, entitled "The Alternating Time Mu Calculus with Disjunctive Explicit Strategies," co-authored by Lutz, Schröder, and Dirk Pattinson. Please, Merlin.
Okay, then welcome to my talk. The title is the name of the logic, the alternating time mu calculus with disjunctive explicit strategies, which is quite long. So what are we actually talking about? What are the structure we want to reason about? We are talking about concurrent game structures. So these are games with multiple agents where at each step, every agent chooses a move from his own set of moves, and the combination of the chosen moves then determines the state reached in the game or the outcome. And the agent, given that every agent chooses a move in parallel, this is why it's called a concurrent game. So in particular, moves of one agent can't depend on a move another agent plays because they all choose in parallel. So if we look at this example game here, we have two agents. Each agent can choose between a move 1 and a move 0. And then the result is basically the parity of their moves here. So it's quite a simple structure, but it's quite an interesting structure. And what do we want to reason about in these structures? Well, the thing we want to reason about is the power which certain players have. So what properties can a player enforce against the choices of the other players? And then it's only logical to say, well, what happens if players choose to form a coalition working together and coordinate their move choices? How does that affect their power? So this is what we want to reason about. And I mean, this isn't new. There are previous work on this, and there are already a lot of logics for making this kind of strategic reasoning. So we'll quickly look at the few we are most closely related to. For the other ones, you can look into the paper. So we'll start at the alternating time temporal logic, which allows expressions of the form that a coalition between A and B, for example, can collaborate to ensure that in the next step a certain property holds, or a certain property always holds, or one property holds until another property holds, and things like that. Then one interesting extension is ATL with explicit strategies, which furthermore allows to predicate those assurances by restricting another coalition to play according to a certain strategy by adding these strategy symbols to the modalities. Another extension from ATL is the alternating time mu calculus, which adds real fixed points to the logic and thereby allows more fine-grained control over the temporal aspects of the expression. And for example, now you could express things like in every second step something holds. Now it's only logical to say, well, why not have both of those, which is what we did, arriving at the alternating time mu calculus with explicit strategies. But then you really would, it's quite restricting the opposing agents C and D here to a single strategy. And it would be nice if they still have some kind of choice, but a restricted choice, which is what Dirk Walter already said in his PhD thesis, but nobody did up until. So we extended this further with disjunctive strategies, where now we don't restrict only to a single strategy, but the agents can still choose from a set of strategies to play. Now, this is all rather abstract. Are there actually interesting properties we can specify now? So, for example, we now could specify that ECC memory can ensure that the stored data is not corrupted, provided that in each cycle the environment flips either 1 or 0 bits. So here the coalition would be the ECC memory, and the restricted opposition would be the environment, which are restricted to either flip 1 or 0 bits. Or another example, no matter what an attacker tries, the intrusion prevention system can always drop suspicious packets or block his IP address to prevent illegitimate access to company resources. Here the coalition would be the attacker, and the opposition, which is restricted, would be the intrusion prevention system, which is limited to either drop suspicious packets or block his IP address. Now, naturally, you would ask, well, at what price what do we pay for these extensions? How about the complexities? So as a starting point, the complexities for ATL and the AMC, we see that both are X-time complete, and also all the extensions are X-time complete. So we don't pay a price in that regard. And model checking see from the ATL to the AMC, we pay a bit of a price, but then we see, well, here we don't pay additional price. So add strategies doesn't add complexity here. And in our case, adding to the AMC also doesn't add complexity. You might notice that here we have two variants of the model checking problem now, because given that we now have these strategy symbols in our logic syntax, we can define two variants of model checking, where depending on if the interpretation of these strategy symbols is to be given to the model checking algorithm, or if the algorithm can decide how those are to be interpreted. In the case where the model checking algorithm decides this, we basically have the same model checking complexity as ATL-ES. Otherwise, we have the same as AMC. And a note here, this QP is quasi-polynomial time and not the quantum polynomial time. Now let's look at those logics a bit closely. What is their syntax? We look at the AMC because, as the name suggests, our syntax is quite closely related to this. So it's parameterized over a set of atoms, a set of agents, and a set of variables. And then, as you would expect, we have the atoms just in the logic syntax and the variables which are used for the fixed points. And we have these two modalities parameterized over a coalition, which is simply a subset of the agents to be read as coalition C can enforce phi or C has to tolerate phi. And the mu and nu are standardly the least and greatest fixed point. So if we add our disjunctive explicit strategies, well, of course, we need symbols for the explicit strategies, and we need those for each agent. So each agent has their own. And those next step modalities now additionally have this set O, which for a coalition D specifies a set of joint strategies they can choose from. So this is basically a set of tuples where each position in the tuple corresponds to one agent and specifies a strategy for that agent. Furthermore, we expect C and D to be disjoint. This is for simplicity, basically, and if Z and D overlap, you could encode it out of the modality, so we don't lose expressivity here, but things get nicer to write. Those modalities now are to be read as coalition C can enforce phi if agents in D pick a joint strategy from O, basically. Apart from that, our syntax has one further restriction. So these boxes and diamonds are called a grand coalition modality if the coalition and the opposition we restrict together are all of the agents. And such a modality is called non-disjunctive if this set O, the disjunctive strategy, really is only a single move, so a singleton set, and hence isn't disjunctive. And grand coalition modalities are restricted to be non-disjunctive. This might seem rather restrictive, but it's worth noting that ATL-ES, which was the only, the logic we built upon with explicit strategies, doesn't have grand coalition modalities at all because they don't consider the set of agents fixed, but assume an unlimited amount of agents, and hence you can't write down such a grand coalition modality. Now, how do we arrive at our results? Well, we use the framework of coalgebraic modal logic, which is an abstraction over modal logics, where the semantics are captured by F coalgebras for a functor F, which are simply a set of worlds, and a transition map gamma, which assigns to each world a set of structures successors, and the functor F captures the structure of our model. And then the syntax is parameterized over a set lambda of next step modalities. So they do exactly one step on these transition maps. And they are supposed to have finite arities. And then our syntax looks very close to the AMC. But now, instead of having this concrete C can enforce and C has to tolerate, we simply have those next step modalities from our set lambda applied to the relevant number of arguments. You might also notice that the atoms are missing here. That is because the atoms can be treated as nullary modalities and hence don't need special treatment in the syntax. And then to give the whole thing meaning, we need to define those predicate liftings, which interpret the effect of such a modality as a subset of these structured successors, given basically the extension of the formulas under the modality. And it's worth noting that here our syntax and the semantics together are only parameterized over a functor and these next step modalities. So in particular, the fixed points are already given in there. And so we don't, to use the results, the generic results from coalgebraic modal logics, we only need to treat these one step things, because everything else is handled in generality already in previous results. So one of the tools we use here are so-called one-step tableau rules, which are tableau rules of the following structure. So we have a premise, which is basically a formula or a set to be read conjunctively of next step of one-step formulas. So formulas where each variable occurs under exactly one modality. So no nested modalities and no straight up variables, only modalities with level 1 basically. And then we have multiple alternative conclusions, which don't contain any modalities at all anymore. So they basically strip off this one step of modalities. And if we find such a sound and complete tableau rule set, which is furthermore extemp tractable, we get the results we have. So that the mu calculus has x-time satisfiability, and we get two variants of model checking, one having NP intersected with co-NP complexity, and one in quasi-polynomial time. And we also get a bunch of other results regarding nominals in the logic and whatnot, but you can look that up in our paper. Now, this is all pretty general. Let's look how it actually, if we treat the AMC in this framework. So we said to capture the structure of our models. So here we defined this functor G, which we can basically read off the normal model structure and only treat one step. So if we recall, our concurrent models had a set of moves for each of the agents. So each world here gets assigned a set of moves for each of the agents, which are simply, for simplicity, just natural numbers. And we expect them to have moves from 1 to that number for simplicity. And then we said, well, everyone picks a move and we get a result. So we have this outcome function, which gets a move of each of the agents and then produces a result world from the set X we pass to the functor. So it's quite easy to see how that corresponds to our concurrent structures. Then we said we need a predicate lifting to capture the semantic. For example, here that the coalition C can enforce that we land in a world of the set extension Y. Well, how do we do that? Well, there has to exist a move for the coalition C such that for all moves of everyone, as long as the coalition C plays the move they picked here in this total move, then our outcome should be in this world. So you see how that corresponds to the normal semantics. And then we said, now we need to find these one-step tableau rules and gain out all these nice properties. So these rules, it's worth noting, we have one rule which is basically simply a simplified form of the second rule. And the intuition for this rule is that we have this one special diamond, and here a bunch of grand coalition diamonds. In this setting, if you dualize the semantic from here, a diamond for the grand coalition basically expresses a necessary truth, because it says everyone has to tolerate that in the next step C1 holds. And the intuition for this rule is that those coalitions D can all play their witnessing move, resulting in A1 together. and together with these necessary truths, they give a reason for why this should be the case. So that's the intuition for this rule, and therefore we have these side conditions basically ensuring that those can play their move together, and that furthermore it's compatible with this one special diamond. So now, how does all of this change when we add our disjunctive explicit strategies? Well, the functor, of course, needs now additionally to be able to capture the interpretation of our strategy symbols into concrete move choices for the agent. So we simply add this function iota, which interprets those move symbols into moves that the agent actually has at that point. And then we need to extend our lifting. And here things stay pretty much the same, apart from now we additionally pick one of those joint strategies and now require that not only the move that the coalition C has chosen, but also the interpretation of the move here, so part of this move. So this seems all pretty easy, but the tableau rules get a lot more complicated. So, but the interesting part here is, so we also have this other rule, which is just a simplification of this rule. So I left it out for now. But we can see that this still has the same structure as the one for the AMC. So we still have these bunch of diamonds, this bunch of boxes here, and we have this one special diamond, and we have these grand coalition modalities. Difference worth noting here is that previously those grand coalition modalities simply expressed necessary truth in the next state. Whereas now, given that our grand coalition modality is defined as the coalition plus the opposition together are the whole set of agents, now they basically express that all the agents without the opposition here have to tolerate that C1 holds in the resulting state, but even if they are restricted to the single move, or in other ways, it expresses that this move suffices for H1 to ensure C1. So, and here, if those were disjunctive and not disjunctive, we have the problem that it then says, well, one of these moves or all of would suffice to reach the C1, but it's not clear how to combine them. And we said the intuition of this rule before was that we combine all this contextual information here and here to give a reason for this diamond. But if it's not clear how these are to be combined, this is an issue. And hence the special role of the grand coalition modality, and hence the rule why we had to restrict us syntactically here. And here, if we recall what such a diamond means, it means, well, the moves in this set suffice for this coalition to ensure this against them, basically. And now it's also worth noting that now we have multiple conclusions. So also in that regards, we get much more complicated already. And we have these index sets here, which basically choose the relevant contextual information necessary for this specific move from the set Q. So it gets a lot more complicated, and there are also many more side conditions than in the previous rule, but that is also due to the fact that now we have a lot more symbols and sets in this rule which need to interact nicely. So for the details, I refer you to the paper. And the time is nearly up, but we still have time for this short recap. This was the alternating time U calculus with disjunctive explicit strategies by myself, Merlin Göttlinger, Lutz, Schröder, and Dirk Pattinson, where we introduced the logic AMC-DES with the same name, and an extension of the AMC as well as ATL-ES, furthermore allowing disjunctive strategy specification. And through the framework of co-algebraic modal logic, we get X time completeness of satisfiability and NP intersected co-NP model checking, as well as quasi-polynomial model checking for the fixed strategy interpretation. And in the open strategy interpretation, which basically uses the same trick as ATLES, simply guessing the strategy interpretation, we get NP model checking. So thank you, and I'm open for question.
Thank you very much, Merlin. So now it's time for questions. Who wants to ask a question here? Okay, so we don't have questions for the moment. Please think hard for things that you would like to know. Okay, so on my side, I'm getting back to the very beginning of your talk, where you gave very quickly, for as far as I could get, the motivation for considering disjunctive strategies. Can you explain for this need? I mean, yeah.
So you mean here?
Yes.
Well, the need, if you restrict the opposition to a fixed strategy, it basically means they have no choice anymore. So this is quite a hard restriction on them. And if you think in normal expressions, people rarely, it's rarely interesting to reason about if another agent is or another set of agents is restricted to just a single strategy, but it's more closely to say, well, they probably will choose one of those, but we still can do this. So yeah, hence also why it was already suggested in the PhD thesis of Dirk Walter to do this, but
so
nobody.
This is due to the fact that you now have explicit strategies, right?
Yes, the explicit strategies
so
are.
You want to open the I would say to the degree of freedom of picking a strategy for the opponent.
Yes.
Right. Okay, yes. I see. Okay, thank you. So who else wants to ask a question? So yes, my question is, I have another one, which is about on the technical level, traditionally, so ITL only talks about propositions, right, on states. And so my question is, how do you, even if for the case of only explicit strategies or explicit strategies are not necessarily disjunctive, how do you correlate states and actions in this setting of the logic? So you have modalities for actions, or do you have? Can you just remind me your syntax? What I mean is that how do you handle strategies and moves in this picture?
Yes, so the strategies are just symbols which can be seen as basically names for strategies which then assign to every world a move choice for the agent, basically.
Okay.
Because they get interpreted as basically a function from agent to moves at the respective world.
Right. And when you interpret strategies, so they're given by the moves, right? That are given explicitly in your concurrent game structure. Okay.
Yes. So they are always interpreted into moves which the agent actually has at this point.
Okay. Okay. So clear as standard. Okay, fine. Who else wants to maybe ask a question? So we don't have questions for the moment, so I would like to thank you for this talk, and please go and read the paper with this very interesting algebraic approach for this kind of logics. So we now move on to the last talk of the afternoon. So it will be given by Paweł, Parys. So the work is joint work with André, Arnold, and Damian Niwiński, and it is called a quasi-polynomial black box algorithm for fixed point evaluation. Please, Paweł.
Okay, hello. So yes, welcome to this talk. I'm going to present this paper. I'm Paweł Parys from University of Warsaw, from Poland, and as I already said, this is joint work with André and Arnold and Damian Niwiński. Okay, so what is it about? So this work is motivated by recent results in parity games. So there are some, for a long time, there were only known exponential algorithms solving parity games, but recently we have quasi-polynomial algorithms for parity games. And on the other hand, we have this equality, which is written here on the top. So parity games are equivalent to modal mi-calculus. And we wanted to see how these algorithms work for mi-calculus, yes, how they can be interpreted. And moreover, we slightly generalize these algorithms to something that we call black box fixed point evaluation. Yes, so this is the first point here, yes, that we generalize these algorithms a bit from this setting of party games to fixed point evaluation, but we also reinterpret it using fixed points. So yes, so there is this conceptual contribution that we translated to the other setting and some small generalization. Okay, and in this, the advantage of this work is also that we unify two kinds of algorithms for parity games. So there were known two different kinds of algorithms, and we somehow show why how they are similar, and that they are. It turns out that they are quite similar, and we also show some lower bounds for our method using. Yeah. Okay. So what is the problem that we consider? So here the input is a function, a monotone function that takes the arguments. And each of the arguments is a vector of n bits. So it's from 0, 1 to power n, yes? So we take d such vectors of n bits, and we are returned as one such vector. And then it's well known that if we have a monotone function, then we can compute its, then it always has a fixed point, and moreover, it always has a least fixed point and a greatest fixed point. Yes, so this mu here, as you probably know, it's the least fixed point. So in this most internal expression, we somehow assume the other parameters to be fixed, and we just take the least fixed point of the function of the first argument, and then this whole expression, starting from this mu, is again a function that takes all the other arguments. So we can again consider the greatest fixed point on the second argument, and so on. So this is well defined. And in this problem, we want to calculate the result, this whole fixed point. And there is some restriction that the question is how the function f is given. Yes, so here we assume that it is given as a black box where we can only evaluate it. Yeah? So we can ask queries of the form that we give some arguments, some concrete values, and we can ask for the value of the function for these arguments. Yes, so we cannot access the function in any other way. And in the complexity, we essentially count the number of queries to this function, but actual running time will not be much larger. The main cost is in querying this function. Okay, and how is it related to party games? So if we have a party game with n nodes and deep parities, then we can directly translate it to such an expression. This is something well known, but then yeah, this n and d is preserved, and now instead of n nodes, we have n bits here in every of these vectors, and this d number of priorities is now the number of these fixed point operators, or the number of arguments, and f is always of a special form. More concretely, it's every bit of output is either a conjunction or a disjunction of some input bits of some arguments. Yes, but there is also a translation in other direction. Yeah, of course, if f is of this special form, then we can just go back. But for an arbitrary function, we can also do a translation, but we need the description of this function, and this can be arbitrarily large because we have, yes, we have many such functions, and the description of an arbitrary function can be of exponential size. So we get exponentially many nodes if we want to translate it back for an arbitrary function. Yes, so it's just going back directly gives exponentially many nodes, but anyway, we can solve it as it's shown on this slide. So what is the difference? Once again, so for party games, so first the first difference is that this function is of a special form. Yes, it's given by a party graph, and moreover, in our problem, this function can be only evaluated while when we solve party games, we can a priori we can access this graph in any way. Yes, we can do whatever we want with the game graph. But what we observe in this paper, or it's actually not really difficult to observe it, is that some algorithms solving party games, in particular this new algorithms, quasi-polynomial algorithm, they access the game graph only somehow by evaluating f. I mean, this is implicit there. Yes, they read something from the graph, but what they actually do is they evaluate f for some particular arguments. So we can apply this algorithm for any function f, and by definition they will be correct for party games, but we can observe that they actually work for an arbitrary function, not only for function coming from party games. So in this way, from this algorithm, we can obtain this black box algorithm for this fixed point evaluation problem. So in our paper and also in this talk, I will try to explain why these algorithms work, and we also try to write this in a nice way, so we show some nice proof of correctness of this quasi-polynomial algorithm. Yes, a proof using me calculus, or instead of actually party games. So more abstract way. Okay, so let me recall some previous work. So of course there are many papers on party games, but here I list some recent results. So the most breakthrough result was by this Calde-Jane, Kusainov, Lee, and Stefan, which introduced the first quasi-polynomial algorithm for party games. But then there was a lot of other papers. So the first family of algorithms is grouped here together. I call all of them asymmetric. Actually, it was shown later that they are quite similar, all these algorithms. So these two papers, they show that these algorithms actually do the same, and the common property of the algorithm is that they are asymmetric, so that they analyze the party game from the perspective of one player only, and try to find a winning strategy for one player. And this is the complexity, so it's n to some power logarithm of d, essentially, where d is the number of priorities. And then there was a second group of algorithms which were symmetric, and moreover they were rather recursive. And here the complexity was a bit worse. Here we have additional 2 in the exponent, which is not present here. So it's quadratically worse. And this is hidden. Okay, this is some complicated complexity, but this complexity is actually a size of some object called universal tree, which I introduce on next slide. And in this results on the top, we use 1 universal tree, and here we use 2, and this is the product of their sizes, or size of a universal tree squared. Let me also mention that this fixed point evaluation problem was also analyzed recently by Hausmann and Schröder, and they obtained similar results to our, but the approach is a bit different, but they obtain something quite similar at the end. Okay, so let me come to the algorithm. So first, I'm going to recall the standard algorithms of the exponential algorithm. Okay, so first some notation. So this whole expression that will be evaluated, that we want to evaluate, is denoted this way. And then during this evaluation, what we often want to do is to put some value a for the last argument, and this gives us some new function which has less arguments. Yes, so this new function will be denoted f with such an arrow with a in the subscript. Okay, so this is a function that is obtained by substituting a on the last argument, and this is something that we want to do very often, namely how to find the least fixed point. We start from 0, and then we substitute the 0 for the last argument, and we evaluate the least fixed point that is inside. Yes, so starting from d minus 1. Okay, so the last argument, our convention is that the last argument corresponds to the outermost operator. Yes, so we evaluate the outermost operator, meaning we substitute for the last argument. Okay, so we substitute the 0 for the last argument, and we get some result, and then we substitute this result again for the last argument, and so on. And we have to do this at most n times, when n is this length of our vectors. Because after at most n times, this will stabilize. And for the greatest fixed point, we do the same, but we start from the top. Yes, from 1, which is the vector containing only ones. And now, how to make this algorithm quasi-polynomial? So there are 2 tricks that we have to apply. So first, instead of starting from 0, we should start from some intermediate results. But something which is somehow more important, or maybe equally important, is that we want to perform less iterations, of course, not n on every level of this recursion. And this, to control the number of iterations, we use a structure called universal tree, we just also introduced before. So what are these restrictions? It's something very simple. Such a restricted function is restricted to some 2 values a and b, where a is some lower bound and b is an upper bound. And such a restriction means that we consider this function only on those bits where a is 0 and b is 1. And then the value is actually the value of f. And here, if both a and b are 0, then this function is also 0, and here it's always 1 on bits where both a and b are 1. So we somehow restrict the scope of our vectors. Yes, we only consider this function on these arguments on some bits of this, or maybe of this result. Okay, and when we know when we have such a restriction, we write it here. Yeah, so now this we use this a and b here for the restriction. Yeah, so this is a fixed point again, but on this restricted function. Okay, and how can we evaluate it? We start from the lower bound, and then when we make the next step, we don't have to start from a again, because we already know that this fixed point will be above the previous result, previous approximation, which is a j minus 1. So we may substitute this a j minus 1 for the lower bound. Okay, and the second component is a universal tree, which is defined this way, that it's universal for some parameter n and h if every tree with height h and with n leaves can be embedded in this tree. So for example, we have 2 trees of height 2 and 2 leaves that exist, and then they can be embedded in this tree. So this tree is 2 universal, and there are known constructions of some universal trees. So this is the complete tree where every node has n. Nice, but it turns out that this can be achieved using quasi-polynomial size. There is such a construction which I don't want to explain you. And then using these universal trees, we can parameterize the value by 2 universal trees. And now instead of repeating everything n times, we look into this universal tree, yes, and this this universal tree has, the root has p children. Then we repeat everything p times, but we make the recursive call with uj. So it's the jth subtree, yeah, because the subtrees may be different. And in the jth step, we use uj. And similarly for the greatest fixed point, here we use the second universal tree. So this is the algorithm, which is quite similar to the symmetric algorithm for party games, which is also parameterized by 2 universal trees. And the correctness, what does it mean that this algorithm is correct? It means that this value that is computed here is actually the fixed point that we wanted to compute. And this is true, and this u and v, these 2 trees, are universal trees. The proof is based on 2 notions, dominions and dominion decomposition, which were already known for parity games, but we adapt them for these fixed points. And the proof is then, when we have correct notions, the proof is not really difficult. You can read in the paper. The time complexity is the product of these 2 trees, so it's n with 2 in the exponent. Okay, and now a short slide on the second variant, so on the asymmetric algorithm. So this it turns out that it follows the same general idea as the symmetric algorithm, but we have to speed it up using the idea of Zaid that was already from '96. So this algorithm, this idea was used to decrease the running time from n to power d to n to power d divided by 2. So instead of evaluating recursively everything, we first expand all the greatest fixed points, and we create a large system of equations, of least fixed point equations. So it's important that only least fixed points are left, and then when we only have least fixed points, this can become the solution can be computed quickly. And if we apply the same idea to what we have now, to this quasi-polynomial algorithm, we also can divide it by 2, and the exponent. So this 2 from here disappears. And what we get is actually very similar to the asymmetric algorithm for party games. So this way we have somehow unified, or we have shown a common framework for these 2 kinds of algorithms, which were previously assumed quite different. And we have linked them using a very old method. Okay, there is also a lower bound in our paper, which but this is a lower bound only for the method, saying that if this equality, this correctness holds only if these trees are universal, and it's known that every universal has this quasi-polynomial size. So using potentially some smaller trees, we cannot improve the algorithm.
Okay, Paweł, I think it's time to conclude.
Yeah, it's time to finish, because now I have only the conclusion slide where I have one more open problem. So here it's about a lower bound. Yes, while we cannot rather hope for a lower bound for the problem in general in terms of complexity, but we can hope for a lower bound in the number of queries, which is more a combinatorial problem. Yeah, so this is a question whether maybe it's possible to prove a quasi-polynomial lower bound for the number of queries. The only lower bound that we have is almost quadratic from 2 times 9. Okay, thank you very much.
Thank you, Paweł. So, do you have any questions in the audience? Okay, no one. There is no one. So, may I ask one? So it's about the use of universal trees for controlling the recursive calls, right? This is this approach with universal trees. Can you comment on how powerful it is and how much this can be applied to, I don't know, maybe other settings like. So what I mean is that parity games provide a very particular kind of fixed point computation, right? It's or do you consider that with parity games you capture essentially all kinds of fixed point evaluation one can think of?
Yeah. So these universal trees were somehow invented. For this particular setting of party games, and I don't know about any other application of it, but in some sense, as you said, yes, this fixed point evaluation that we have here is somehow the most general. I mean, you can encode some problems in this. So yes, but. Yeah, I don't know about any other application of this universal trees.
Okay, so maybe to make my question more precise, as you showed, if you have some fixed point evaluation in mind, you may turn it as a kind of parity game, solving some parity game with some exponential blow-up, right?
Yes, but yes. Here we show that actually for every function f, this approach with universal trees works. Yes, so
okay. So this is one of the big message.
This is the maybe one important message of this paper. Yes.
Okay. So there is a question. Alex, you have one.
Yeah. So this is probably a very naive question in a sense. Well, not really naive, but a basic question. I'm just curious, how well do these algorithms perform in practice compared with the earlier iterative algorithms, say, or earlier algorithms?
So I couldn't hear you the whole question, but you asked about practice of solving parity games, yes?
Yeah. So if you apply these to real problems using parity games,
yeah. So it turns out that it's not really good. Yeah. It's people tried to implement these quasi-polynomial algorithms, but okay, for some worst case examples, that they are really faster than the exponential algorithms. But in practice, like when you get a parity game, it's usually very easy in some sense, and the standard algorithms with some heuristics solve them much better than this quasi-polynomial approach.
Okay, I was just curious. Yeah, thanks.
Okay, so we don't have any more questions. So let me close this session. Thank all the speakers for the nice talks. And if you want to unmute and clap, this is very good, encouraging for this remote session. Okay, so let me now invite the speakers and the audience to attend the speakers corner in the CSL social space on Gather. So goodbye everyone, and meet you there. Bye bye.